Force and motion. So first of all, let's understand what a force diagram is. A force diagram shows all the forces acting on an object, and each force is shown with an arrow which will point in the direction in which the force acts. So the arrows that we can see in this diagram here indicates that the object, which is in a circular object there, it has a force acting to the right of 20 newtons, force 20 newtons to the left, 10 newtons acting downwards, and 30 newton acting upwards. Force diagrams are a really important part of solving problems. So let's talk about Newton's first law. So when the forces acting upon an object are balanced, the object is said to be in equilibrium. So in this case, if we take a look at the force acting to the right is 20 Newton and the force acting to the left is 20 Newton. Here the forces are balanced because the total force to the right is balanced by the total force to the left. So we can say horizontally, this object is in equilibrium. But vertically, we can see that there is 30 Newton acting upwards and 10 Newton acting downwards. So vertically, the forces are imbalanced. So therefore, it will be not in equilibrium in the vertical direction. So Newton's first law states that if an object is at rest, then it will stay at rest. And an object, if it is moving with a constant velocity, it will then continue to move with that constant velocity, unless an unbalanced force acts on the object. Okay, so in other words, if an object is in equilibrium, it could be at rest, or it could be that it's moving with a constant velocity. So equilibrium doesn't necessarily mean it's at rest. It could be moving with a constant velocity. So what happens then if there is a resultant force? Well, a resultant force acting on an object will cause the object to accelerate in the same direction as the resultant force. So we come back to this example here with this diagram. Let's take a look at applying Newton's first law here. The diagram shows the force is acting on a particle. Draw a force diagram to represent the resultant force. We've got that. So a force diagram to represent the resultant force. Well, we could have, we've got 20 newtons to the right, 20 newtons to the left. So in this case, the resultant in the horizontal direction is 0. So I'll indicate horizontal, right as positive, and I'll say resultant force in the horizontal direction is equal to 20 minus 20, which is equal to 0. In the vertical direction, I'll take up as positive. The resultant force in the vertical direction for this object is 30 minus 10, which is equal to 20 newtons. So in total, the object has simply a 20 Newton force acting upwards on it. This is the resultant. So the object is moving upwards. It's got a resultant acting upwards. Therefore, the object will accelerate in this resultant force direction upwards. So describe the motion of the particle. It will be accelerating upwards. Now, where we have a resultant force which is not 0, then the particle will accelerate in that direction, as we've said. Now, we can then find out this acceleration using Newton's second law. Newton's second law of motion states that the force needed to accelerate a particle is equal to the product of the mass of the particle and the acceleration produced, i.e. F equals ma, Newton's second law. Note here that the F mentioned in Newton's second law, F is the resultant force, not a singular force. It's the summation of all the forces, the net force, the resultant force. So let's look at the application of Newton's second law. this question here. Question reads, a body of mass 5 kg is pulled along a rough horizontal table by a horizontal force of magnitude 20 newtons against a constant friction force of magnitude 4 newton. So I'm going to start by drawing this object. I'll represent it using a rectangular box here. It's on a surface, so I'll just draw the surface here. It's been pulled horizontally by a force of magnitude 20 newtons. I'll indicate that it's being pulled to the right here by 20 newtons. And there is a constant friction force of 4 newtons. Friction always resists the motion, so it's acting in the opposite direction here, 4 newtons. It says here, given that the body is initially at rest, that means it starts off with initial velocity 0. So here's our force diagram here. Now we need to consider one force is also in the vertical direction. Since it's got a mass of 5 kg, there will be a force of 5g, i.e. the force due to weight acting downwards. But that would imply that the object is accelerating downwards, but there's something resisting it, the surface of the table here. And the surface of the table will exert an upwards force on this object to stop it from going through, and this is the reaction force here. So we've got reaction R there. So now our force diagram is complete. Let's go and take a look at how we would work this question out. Now, as we know, the object is not moving up or down, so the acceleration in the vertical direction is 0. So when we go and solve this, we will apply Newton's second law, F equals ma, but we can apply Newton's second law in the vertical direction, taken up as positive, and I can apply F equals ma in the horizontal direction, taking right as positive. I've taken the initial direction of motion right to be positive for the horizontal case. So what are my resultant forces vertically first? Well, up as positive, so I have R minus 5g is equal to the mass, which is 5, times the acceleration in the vertical direction is 0, since it's not moving up or down, okay, because the object is moving horizontally. This then gives us R is equal to 5g. It indicates what our reaction force is. And that makes sense because it's not accelerating upwards or downwards. Therefore, the resultant must be 0 in the vertical direction, as we can see here. Horizontally, though, we'll take right as positive, so we have 20 acting to the right, then we have 4 acting to the left, so minus 4, so this is my resultant force, is equal to the mass, which is 5, times the acceleration, which we don't know. That's what we're trying to work out. So from here, we can then go and figure this out. 16 over 5 is equal to A. So here we have our acceleration, which you can leave to 2 significant figures, 3.2 meters per second squared. So that's part A of the question. Part B of the question goes on to say, then find the distance traveled by the body in the first 4 seconds. So now, since we're considering distance, F equals ma, Newton's second law, doesn't have any distance quantity in it. So we need to think about applying suvat here, because suvat distance, as long as the object is moving in the same direction, the distance will be the same as the displacement. So for part B of the question, I will go and consider suvat. Now I'm going to consider the suvat between 2 points. The starting point, which I'll label as, let's say, point A, and it will accelerate to the right to get to a certain point B after 4 seconds. So the time it takes there is 4 seconds. So the time there at B is t is equal to 4. So I've indicated that on my diagram just to make it easy for me. So I'm going to consider suvat between A and B, and I'm going to take right as positive. Always indicate the initial direction of motion as positive and indicate the 2 points which you are doing suvat between. Start by writing SUVAT. We are asked to find the distance, which we don't know. Distance and displacement are the same thing, as it's traveling in the same direction as we said earlier. U is initially at rest, so u is 0. Final velocity here we don't know. The acceleration we worked out in part A to be 3.2 meters per second squared, and the time it takes to go from A to B we're given in the question is 4 seconds. So we have 3 quantities given, and we can work out the fourth S. So let's find an equation which relates all of them, and the equation that we've got here is S is equal to ut plus half at squared. Let's substitute the quantities that we know, so 0 times 4 plus half acceleration, which is 3.2, times t squared, which is 4 squared. And then working this out, we get an answer of 25.6 meters. Let's make sure we've answered the question. It's asking for the distance traveled in the first 4 seconds, and that has answered the question. Part C then goes on to ask us to find the magnitude of the normal reaction between the body and the table. Now we've actually done that already here. The magnitude of the normal reaction, we worked it out here. It's asking for the normal reaction, which is this R. So R is equal to 5G. We can work what that is as a value, 5 times 9.8. So this is in fact part C, and this was part A. So 5 times 9.8, and that gives us 49 newtons is our reaction.